All right, in section 2.4, we're going to learn about a graphing method that is probably the most important we'll learn in the course. We'll use it a lot in the future, and it's used a lot in business to figure things out, courses of action, things like that. So let's actually skip down to 33, and then we'll come back and do the other problems. So this whole section, the main theme in this section is what we call a scatter plot. A scatter plot. And a scatter plot, A is the answer to this, so let's just get the answer and then let's look at it. A scatter plot is a graph of paired XY quantitative data. It provides a visual image of the data plotted as points, which helps show any patterns in the data. Okay, so let's first look at this word quantitative data. So quantitative data is data that's measurable and has units. So examples would be height, weight, we could say income, we can measure that with dollars, things like that. The other type of data that we will see in this class, this whole section is about quantitative data, so we're going to live in this world here where it's something that has units and we can measure it. But I'll just introduce it now because we've actually seen it already and it doesn't hurt to show the difference, is qualitative data. So notice the difference in words here. Quantity is the root word of quantitative, so it's a quantity. Qualitative, the root word is quality, so it's a quality or a category. This is not measurable, and it has no units. So, for example, it's things like hair color or eye color would be one, or political affiliation, political party we'll call it. So we can talk about, we might talk about the number of people with blue eyes versus brown versus green or something like that. And we might say, oh, green's rare, and we might be able to do some statistics on it, but typically we can't make statements like, oh, having this eye color is more important or better than having this eye color or something like that. Okay, so it's a type of data that we can do less math with. Okay, now back to our scatter plot. So it's going to have two axes. Let me see if I can borrow some space up here. You have an X and a Y axis. And let's just make up a problem. So let's say we're going to look at people's height, and we'll do that in inches, versus people's weight, and we'll do that in pounds. Both are quantitative. They're measurable. We can get out a ruler or a scale to measure height and weight. And they have units, so inches, pounds. And what I would do is we would just measure. So we'd measure everyone's height, measure their weight, and then each person would have an ordered pair. So they would have an X value for height and a Y value for weight. And what you do in a scatter plot is you plot dots. So a shorter person over here has a lower weight typically. Then we get taller people. Typically, as you get taller, you have more bone mass. You have more, you just have more mass to you to support that height. So you tend to weigh more as people get taller. So this would be the scatter plot. And then a big part of this class is to try to draw a line. And then we try to come up with an equation for that line. And then you can model people's height and weight. So you can come up with a model. Okay, so this is the main topic today, is scatter plot. Quantitative data produces dots, and then later on in the class we'll learn how we're going to use a straight line to try to capture as many dots as we can. And we do this because it provides a nice visual image. So I can quickly see, ooh, there's a pattern here. And that's another thing we'll talk a lot about today is, do I see a pattern of any kind? Show any patterns. Questions about scatter plot? We will see this many times in the course. Okay, let's go back to 31 then. We skipped over that. In this section, we use R to denote the value of the linear correlation coefficient. So R stands for linear correlation coefficient. Why do we refer to this correlation coefficient as being linear? Okay. So R is a measure of how straight of a line those dots are. So I'm going to do a bunch of scatter plots here. They all have X, Y, X, Y. So if, I'm just going to teach this by showing you many examples and you'll catch on very quickly. If the dots in a scatter plot line up perfectly so that I can draw one line that goes through every single dot, that means I have perfect correlation. That means that I can predict perfectly. You tell me the person's height and I can tell you their weight exactly. I won't get it wrong. This is an R value of 1.0. An R value of 1.0 is perfect correlation. Now let me show you the next one. So notice that these dots go up and to the right. If the dots go down and to the right, but they're perfectly on a straight line, this is R of minus 1.0. What do you notice about the difference in those two? One's trending up, it gets a positive value. In fact, we could put a plus here if we wanted to. One's trending down and has a negative value. So we're going to use the slope of the line to indicate is it positive or negative. Now height and weight doesn't make sense here because typically as your height gets bigger, your weight doesn't get smaller, right? But I could do one where I could say car weight, we'll actually see this problem later, and miles per gallon. So typically as your car gets bigger and heavier, your miles per gallon goes down, right? So that would be an example of, we call this negative trend, decreasing trend. Okay, now it gets more interesting when I have things like this. So let's say, okay, the dots are going up and to the right generally, but they're not perfectly on the line. Well, I can still draw a line through this, but my R value now is something like 0.7 to 0.9. So one is perfect. These dots are a little bit scattered from the line, so it's more like 0.7 or 0.9. Okay, let's say the dots get really spread out, but the trend is still generally up and to the right. This is an R value of like 0.3 to 0.5. Part of the challenge here is, you know, you're going to see dot patterns and you're going to have to guess the R value, and it does just take practice. So the more of these you see, the better you'll get at this, but it does take a little bit of time. Okay, now I can have the patterns go down. If they go down, you just add a negative. So these would be R values of negative 0.7 to negative 0.9. So notice it's about the same pattern as the 0.7 to 0.9, but they're down, so we get a negative sign. Okay, the other type you might see is this one. It's literally a cloud of dots. There's no line I can draw lots of lines, but which one's right? This would be an R of 0. So when there's no clear pattern to the dots, it's literally just what we call a cloud of dots. That means there's no correlation, so your R value is 0. What does this mean? It means that you tell me your height, I have no clue what your weight is. There's no pattern for me to predict it. Okay, maybe the only other, no, I won't even show that one. I've showed that one in the past, but it doesn't offer a lot of value. So these are the cases we're going to study, things like this. And we're going to have to try to figure out, is there no pattern? R is 0. Is there a perfect pattern up? Is R is 1. Perfect pattern down, R is -1. And then are we, how far off of perfect are we? Notice that your R value never goes, it's always sandwiched between -1 and 1. So you'll never have an R value of 2 or -3 or anything like that. It's always going to be either -1 or +1 or any decimal value in between that, including 0. Okay, so let's look at this question now. In this section, we use R to denote the linear correlation coefficient. Why do we refer to this correlation coefficient as being linear? The term linear refers to a straight line, and R measures the fraction of the points the best line passes through. So notice on this one, if this was true, fraction of the points, I told you that this line would have an R value of 0.7 to 0.9, but I literally only hit 1 dot, maybe 2, out of like 10 that I drew there. So if I only hit 2 dots out of 10, that's 20%. Well, I'm telling you that this is 70 to 90%. So clearly, it is not the fraction of the points. The term linear refers to the straight line that passes through the greatest number of points, and R measures the fraction of the points the line passes through. We just argued that it can't be the fraction of the points. The term linear refers to a straight line, and R measures how well a scatter plot fits a straight line pattern. That's correct. The term linear refers to a straight line that passes through the average values of the paired data, and R measures how well a scatter plot fits. We're not looking at the average values of the data, we're looking at the data. We'll learn this later on, but what R actually measures is the vertical distance between each dot in this line, which is called an error. And then we try to minimize that error with a formula that's pretty complicated, but we'll let the computer do the work for us. Questions about R? Having these pictures and kind of studying these pictures will really help you learn it, because hopefully there's a pattern here you've picked up on, and then it becomes pretty simple if you kind of get the pattern. Okay, what's that? So there's 2 measures for linearity. It's R, or what we call R squared, where you just take this number and you square it. So you take it to the second power. But for the most part, we will study R. Okay, 32. If we find that there is a linear correlation between the concentration of carbon dioxide in our atmosphere and the global temperature, does that indicate that changes in the concentration of carbon dioxide cause changes in the global temp? So what they're saying is this. We look at carbon dioxide, CO2, and we look at global temp, and they found that the dots look something like this. So R value of maybe 0.8, maybe 0.9, pretty high. Can we say then that more CO2 causes higher temp? higher temp? Now, before you answer that, I'm going to show you another one that's maybe easier to analyze, and it's a real one I've seen. And you can look this up, and you can find data that proves this to be true. And that is this. You can prove that as ice cream sales increase, shark attacks increase. And it's pretty solid linear relationship. It's like R of 0.9 or something. And then I can say ice cream sales cause shark attacks. More ice cream sales cause more shark attacks. This is a famous example. Can we say that? The plot tells me I can say it, looks like it, but let's just think about it logically. Does selling ice cream really cause sharks to attack more? What's more likely the reason that there's a correlation, there's a connection? And that's all that correlation tells us is correlation is simply, is there a connection between these two variables? Well, is there a connection that you can think of that would relate ice cream sales to shark attacks? Garbage? Okay, in what way? So garbage in the water or something is pulling the sharks in? Okay, maybe. What's another one?
Getting hot out, people are going to buy ice cream, and they also go to the beach to cool off and water their sharks.
Don't we think that's the more reasonable explanation? When do people buy most of their ice cream? In the summer. What do people do mostly in the summer? Swim. And if they're near an ocean, they're probably swimming in an ocean. So it's probably more likely that the reason you're seeing more shark attacks is simply because people are in the water more because it's warmer. Okay? And that leads us back to this one. Just because there's a connection does not mean that one causes the other. Okay? You cannot say that. In fact, this is famously stated like this: correlation is not causation. Exactly right. So you've heard it before, so it is kind of popular. And you can find really interesting ones. Like I've seen ones where they show bee populations increasing causes cancer to go up. I've seen ones where they'll say number of tornadoes causes births to go up. You can find data that supports lots of silly things. And so as smart statisticians, what we have to do is say, okay, there's a connection between CO2 and temperature, right? I can say that. There's a connection between CO2 and temperature. Does this cause that? Maybe, maybe not. But hey, there's a connection there. So, okay, scientists, go figure it out. See if there is a scientific theory or something that proves that CO2 does cause temperature. But as stats folks, all we're going to do is say if there's a connection or not. Okay, this is getting pretty muddy. Let's see if we can. So, what was the question? Does that indicate that changes in the concentration of carbon dioxide cause changes in the global temperature? No. So we're never going to say that one thing causes the other. That might be the easiest thing to remember. In this class, we are never going to be able to say this causes this. What we can say is this correlates with that, which means they're connected somehow. Okay, I think we might have gotten all the tough theory out of the way. Questions on this? This is where the class starts to get harder, right? So the first 2 chapters were pretty easy, but this is starting now to get into the more complicated stuff where we have to think a little bit more carefully about what's going on. Okay, in the next one, the table provided below shows paired data of the heights of a certain country's presidents and their main opponents in the election campaign. Construct a scatter plot. Does there appear to be a correlation? So they basically did president's height, which they can do. It looks like they did it in centimeters here, versus their opponent's height in centimeters. Doesn't matter the unit, just as long as you have it be consistent. So it's height versus height, two quantitative variables, so that's perfectly reasonable to do that. Okay, so here's the table. Now, you have to take these data points, so these are X values here, these are Y values here, and because it's a big table, they have to split it into two different groups. So you have to basically match all of these, so these are matched, these are paired, and you have to take all these numbers here and all these numbers here and plot them with their X and Y coordinates. That would be quite a bit of work to do by hand, right? And I will never ask you to do something like that by hand unless it's a really small problem, like maybe 6 or 10 data points and you could do a quick sketch of it. So here are the steps, because you're going to have to do a problem like this on your homework, and you're going to want the computer to do it for you. So here's how you have the computer do it. So when you see this problem online, there should be a button that looks like a table, like that. You're going to click that. And that's going to load up this table here. Then on the top right of this table, there'll be this little symbol that says that has a window in a window. And you're going to click that. And there'll be options. There'll be 3 options. You want the option that says open in StatCrunch. And then once you open in StatCrunch, it'll basically look like Microsoft Excel, if you know what that looks like, where it's a bunch of cells, right? Bunch of lines and lines. But in there, there'll be a button called Graph. You'll click that. Then after you click Graph, there'll be an option that you can see that will say Scatter Plot. You'll click that. Then you will go and you will click on what says X variable. And you'll have 2 options for the X variable. You'll have president's height or opponent's height. You will click on president's height. Now, almost always in this class, the first column they give you is X, and the second column is Y. So X is president's height. And then you'll click on Y variable. Well, for this problem, the Y variable is the opponent's height. So it'll say opponent's height. And then there'll be a button called compute. And once you click that, see if I can get all the instructions on one screen. Once you go through these steps for this particular problem, now the numbers for each student are a little different. So yours might be different than what this one shows. But for these numbers, the plot that it will produce is D. And that's really the most important part of this, is getting the plot. Because once I have that, now I can start to say, is there a pattern? What's the R value? We can start to look at the more important statistical aspects. So for this one, would we say there's a correlation? So for there to be a correlation, it has to be close to a straight line, which means your R values have to be close to either 0.8 or more, or negative 0.8 or less, right? Well, so that's if you know the R value. But if we just look at this in general, do we see a pattern here? Maybe you see a pattern. Here's how I like to think about it. Let's actually look at C. If you got C as your graph, would you say there's a pattern? A straight line pattern, that's the key. It has to be just one straight line. Here's how I say it. the way I look at it is, if I had each of you come up here and draw a straight line, I think you would all do this, right? Pretty much every single one of you do something like that. If I asked each one of you to come up here and draw a straight line, isn't it reasonable to say, well, somebody might do this? Maybe you see it that way. Maybe you see it this way. Maybe you see these dots as lining up, right? The second I get more than one possible answer, then we're game's over, because I need you all to come up and draw pretty much the same line. Then I know, yes, that's a correlation. I think you would all reasonably come up and do this one, right? But this one, again, I don't know, you might do this, you might see these, you might see those. So A and D would be no correlation, B and C would. But ours was D, so we would say, no, there does not appear to be a correlation. And again, I know this is a bit tricky because you might all do it a little differently. So it's just going to be one of those things where it's going to take practice and you'll get it. Okay, 35 is a very similar problem. You're going to have to use these same steps. So in this class, I show you the steps one time. So you want to copy them down. And then you'll end up using those same steps over and over. So those same steps will be used for 35 to construct the data set of, construct a scatter diagram using the table. This data says from a study, amount of tar and carbon monoxide in cigarettes. Use tar for the horizontal scale and carbon monoxide for the vertical scale. So they want us to look at tar on the x-axis, and they want us to have carbon monoxide on the y-axis. And so once again, they gave tar first because that's x, and then CO is second column. And just notice, this is meant to be one big table, but it's too big, so they split it into 3 chunks. Okay, so if you follow the steps I just wrote, the scatter plot that the computer will produce for this problem is A. Correlated? Yeah, everyone can see one line there. I think it'd be reasonable. We'd probably all come here and do this, right? So I think we'd all reasonably get to this line. So yes, it is correlated. Yes, as the amount of tar increases, the amount of carbon monoxide decreases. So be careful. This says the opposite. We already said no isn't right. Yes, as the amount of tar increases, so from left to right, carbon monoxide also increases. So it gets higher. I should probably have stated that when I first showed you this. If your pattern is like this, this is increases, increases. So as X increases, Y increases. This one's the opposite. If you have this pattern, it's still increasing X, but it leads to decreasing Y. This one's called proportional. This one's called inversely proportional. A lot of theory today. More theory today than we've seen in the entire class up to this point, probably. Questions? I don't want to lose you. This is where we start to get a little trickier stuff. Okay, if we're good with this, let's try 36. So 36 is going to be the one that I already did. It's the weight of your automobile and the miles per gallon. And this is one that I would reasonably expect you to be able to do by hand. Let's say if I gave you a test question like this. There's only 7 data points, so it wouldn't be that hard to plot. But you can just follow the steps from the other problem and have StatCrunch do it. If you have StatCrunch do it, the correct answer for this one is D for the plot. Correlated? Yes. Absolutely. In fact, this is probably the best one we've seen yet. I can draw one line and it hits almost every dot And I don't think any of you would draw the line much differently than that. So is there a relationship? Absolutely, yes. So get rid of these two no's. As the weight increases, the highway mileage decreases. So it's down and to the right, so that's an increase-decrease pattern. So it's A. And that one should also pass the logic test, right? I mean, we don't expect these huge cars to have better gas mileage than these tiny little smart cars, right? Okay, so those are, once you know how to plot them on the computer, those aren't too bad. 37 is a bit different. It's got, so for a data set of brain volumes in cubic centimeters and IQ scores of 10 males, notice N here is only 10. That's a little bit of a small sample size. Normally we would say that's less than 30. We shouldn't even do any math on it, but we'll let it slide. And the reason we're going to let it slide is they want the sample sizes to be small in these problems so you don't have to do as much work. The linear correlation coefficient is R is equal to 0.296. Notice that's a very low number, which means that the pattern, it is up and to the right because it's positive, but it's probably pretty cloudy, right? It's probably something like this. Because these dots, if this isn't close to 1, these dots are not close to a straight line. Use the table available below to find the critical values of R based on a comparison of the linear correlation coefficient R and the critical values. What do you conclude about linear correlation? The first part of these problems is very easy. And I have students that struggle with these problems on the homework, but let me just show you, the first part should be simple. If N is 10, you just go to the table for N equal to 10, and you take whatever number is across from it here. And you just kind of have to remember this. These problems are generic, so they want you to consider the fact that maybe this could have been, instead of up and to the right, it might have also been down and to the right. So the answer for the first part, the critical values are, it's this number, but one's negative and one's positive. So you have to put two answers there. This number, one where it's negative, one where it's positive. Now here's where it gets a little trickier. For the second part of the problem, you have to draw a number line. You don't have to once you understand the concept, but I'm going to draw a number line just to help us out. And you're going to plot these, you're going to first plug in here to the far left -1 and 1. Because this plot is R values. R has to be between -1 and 1. Then you're going to plot these critical ones. So I had one critical at -0.6 about here, and one at 0.632 about here. Now, if the R value they gave you is in between these two critical values, then you're going to say that there's not evidence of linear correlation. Okay, so you're going to plot this R value on this number line. If it's in between these two, then it's not evidence of linear correlation. If it's in this region over here, or this region over here, that is evidence of linear correlation. So the only other step to this problem is to plot our R value and see, is it in this part, or the middle part? Well, an R value of 0.296, almost 0.3, would be right about here. So here's your 0.296 R. And hopefully you can all see that it's clearly in the not linear range. So Another way you can just think about it, if you want to think about it real quick, if R is between these two numbers, not linear. If R is outside of these two numbers, there is linear evidence. So for this one, since the correlation coefficient R is between the critical values, we would say there is not sufficient evidence to support the claim of a linear correlation. So basically, this sort of problem allows us to make that correlation analysis without the plot, without looking at the scatter plot. Any questions on that one? Okay. Next one's exact same, just different numbers. So this is chest sizes of bears and their weight. 5 anesthetized bears with a linear coefficient of R is 0.905. So first thing, 5 bears, N equals 5. So we go to the table, N equals 5, we're here, which means we grab these two numbers, this number here, and then the first answer is this number with a negative, then that same number as a positive. So those are the critical values. Now we just have to compare 0.905 0.905 is bigger than 0.878, so it's right about here. That's the R value. And you see, hopefully, that it's outside of this middle part. So if it's outside of this middle part, we would say there is sufficient evidence. That's the second part. The first part says, since the correlation coefficient is between, it's not between. In the left tail, this would be the left tail. This would be the right tail. It's in the right tail. Then because it's in that right tail, there is sufficient evidence of linearity. Yep, so if it's outside of this range of critical numbers, there is correlation. Okay, 39. For a data set of brain volumes and IQ scores of 5 males, the linear correlation coefficient is found and the p-value is 0.604. Write a statement that interprets the p-value and includes a conclusion about linear correlation. The p-value is something we're going to study more in the future. It's a probability, and probabilities go between 0% and 100%. But basically, I'm just going to outline it very simply here. So a high p-value. We consider a high p-value something that's bigger than 0.05, which is 5%. If the p-value is bigger than 0.05, then there's not evidence of linear correlation. So this is just another way to figure out if it's linearly correlated or not. Bigger than 0.05, not evidence of linear correlation. A low p-value is less than or equal to 0.05, 5%. So it's smaller than this number. That is evidence of linear correlation. So all we have to do is look at our p-value. It's either going to fit into this one or this one, and then we know the answer. So 0.6 is bigger than 0.05 or smaller than 0.05? Bigger, clearly. 0.6 is bigger, therefore there's not evidence of linear correlation. So this p-value is, oh, first they want you to convert it to a percentage. So hopefully everyone can see that 0.604 is 60.4%, which is high. So there is not sufficient evidence to conclude that there's linear correlation. If we can do 39, 40 should be pretty simple as well. They give us fuel consumption for cars based on how heavy they are, so we already saw that problem. P-value is 0.017, which is, move the decimal 2 to the right, 1.7%. 1.7% is less than 5%, so this is low. If it's low, that is evidence of linear correlation. Questions here? Okay, so you're now able to complete chapter 2. That's due this Sunday.